Hello everyone. In this lecture, we will study an important object in graph theory. This is trees. So we first consider the following question. Suppose G is a graph or general graph with order n. Okay. And suppose G is connected, then what is the lower bound for the cardinality of the edge set? In other words, how many edges you will have at least. And if you draw some examples, you will find that probably we have a lower bound n-1. So we will show that this is actually holds. This holds. Okay, then we prove by induction. We prove this by induction. So when n equals 3, 1, 2, 3, we can just verify it manually. Okay, now suppose theorem holds for all n equals k greater than or equal to 3. Okay, and then consider a general graph connected graph. G equals VE, where the cardinality of V is k plus 1. Okay, then without loss of generality, we can assume G is a simple graph. As we said before, if it's not simple, then you can take its reduction. So just like we discussed last time, you map to G prime, which has the same vertex set, and for the edge set, you just change the multiplicity of each edge to 1 reduction. So this is simple graph. And if you check the connectivity of the graph and the simple graph, you will see after reduction, connectivity doesn't change. And then you reduce the cardinality of the edge set. So we can consider the worst case when G is a simple graph. Okay, now let G theta equals V theta E theta be a maximal connected subgraph of G such that the edge set is greater than the cardinality of the edge set E theta is greater than or equal to cardinality of vertex set V theta minus 1. So here, maximal means that this is a partial order, just any subgraphs G theta contained in G prime contained in G implies that G theta is G prime. This is a maximum mean. That means there's no subgraph has G theta as a true subgraph. Okay, so I leave to you to understand what does maximum mean, and then we claim that to prove the theorem, it suffices to show the following claim: G theta is G. So if G theta is different from G, then there are points X in V, get rid of V theta, Y in V theta, and an edge XY in E. Then G hat equals V theta union Y union X, E theta union the edge XY is a connected subgraph OG such that E theta coordinate is greater than or equal to coordinate of V theta minus 1. So this is a contradiction. Okay, so therefore we prove the theorem. Oh, sorry, here I should symbol any subgraph here. So maximum means any subgraph G theta contained in G prime contained in G satisfy this inequality star implies G theta is G prime. That's exactly what does the maximum means. Okay, now look at the following two examples. So suppose you have four vertices, and by the theorem, at least you need three edges to make it connected. So here are two typical ways to do that. And then we have the following definition. A connected graph is a tree if the above inequality becomes equality. So the inequality side holds, the equality side holds. So, or you can say in this way, the most efficient way to make a graph connected by adding edges. Okay, next, in the following, we will give several equivalent definitions of trees, and in reality, for different questions, different characterization have different advantages. So that's a typical phenomena or typical strategy in mathematics. Usually for some important concept or formula or theorem, you give different equivalent versions, and then for different cases you use a different version to deal with that. Okay, then theorem A says a connected graph is a tree if and only if each edge is a bridge. So recall that in the definition of tree, we count the number of edges. And here we use a different characterization. We don't care about the total number of edges. We care about with this edge and connectivity with and without this edge. So that's a bridge. So bridge means after remove this edge, the connected graph becomes disconnected. And we proved last time, when you break a bridge, the connected graph will have two connected components. Okay, so here since we have if and only if, we prove two directions. So we first prove that if G is a tree, then if a connected graph is a tree, then each edge must be a bridge. So let alpha be an edge of a tree. Consider G prime. G prime defined by removing alpha from the edge set, then by theorem. So the theorem at the very beginning, G prime cannot be connected. This is because now the coordinate of the edge set of G prime is coordinate of V minus 2. So according to the theorem, which says if you have connectivity, then the edge set has a lower bound. The coordinate of edge set has a lower bound. Coordinate of vertex set minus 1. Okay, so then alpha is a bridge. Okay, now next we prove the other direction. If G is a connected graph such that each edge is a bridge, then we are going to show that the coordinate of the edge set is the coordinate of vertex set minus 1. So for convenience, let's assume the graph is of order m and prove by induction. So when n is 1 or 2, we can verify it manually by the connectivity that theorem A holds. And now suppose, so let's call this green star is true for n less than or equal to k, where k is greater than or equal to 2, and then consider the case n equals k plus 1, let alpha be an arbitrary edge of G. Now consider a subgraph derived from G by removing alpha. Then G prime has two connected components. This is a result we proved last time. So G1, V1, E1, G2, V2, E2, and it is easy to show that. Actually, this is a crucial thing, but you need to verify it. Although it's very easy, each edge of G1 is a bridge of G1, and each edge of G2 is a bridge of G2. So noted that originally we only know that each edge of G is a bridge of G. So you need to apply this property to show that for these two subgraphs, you still have the bridge property. Otherwise, you cannot do the induction. Okay, suppose this is done, then by induction, G1 and G2 satisfy the conditions. Therefore, we have the equality. E1 is V1 kinetic minus 1. Kinetic of E2 is kinetic of V2 minus 1. And then kinetic of E, by our construction, is kinetic of two subgraphs plus 1. This 1 corresponds to the edge alpha, and the kinetic V1 plus kinetic V2 minus 2 plus 1, which is kinetic V minus 1. Notice that when we remove the edge alpha, we never remove the vertices. Okay, so the vertex set just split into V1 and V2. Okay, then we complete the induction and prove that prove theorem A. Okay, and although theorem A is a little bit complicated because that requires you to test if each edge is a bridge, but then immediately corollary of this is another very nice characterization of the graph of the tree, for which you don't need to count the number of edges. So this is the following equivalent definition of tree. Theorem B. Suppose G is connected, then G is a tree if and only if G does not have any cycles. So prove. Of course, here you also have two directions. We first prove that if G contains a cycle, then G cannot be a tree. So if gamma is a cycle, then each edge of gamma is not a bridge. So actually we proved this before and leave it to you. Think about why this is true. Okay, and then the other direction, which means that if you have the property that there's no cycles, then you need to prove this connected graph is a tree. The other direction follows from the next lemma. So here's a lemma. An edge alpha of a connected graph is a bridge if there does not exist a cycle containing alpha. Okay, so if you get this lemma, then because there's no cycles at all, then each edge must be a bridge. Then by theorem A, we can derive that the connected graph G is a tree. Okay, and now let's prove it. Suppose there is no cycle containing alpha equals xy. If alpha is not a bridge, then there is a path in the subgraph G prime defined by V, E, get rid of alpha, joining x and y. So let it be gamma x, x1, x2, blah blah, xm to y. Then consider x, x1, x2, blah blah, xm plus y. This is gamma. And then you add alpha to it. Then this is a cycle, which is a contradiction. Okay, so we prove that if there's no cycle containing alpha, alpha must be a bridge. Okay, therefore we complete the proof of theorem B. Okay, next we have another very interesting characterization of tree. This is by the distance property. So a graph G is a tree if and only if every pair of distinct vertices x and y is joined by a unique path. So we first prove that if G is a tree, then it shares this interesting property. So if G is a tree, then there is a path connecting every pair of vertices. Moreover, so this is existence, then we need to show that it's unique. Moreover, if there are two paths, then there is a cycle which contradicts with theorem B. Theorem B tells us that for a tree, no cycle can exist. Okay, now suppose we prove the other direction. Suppose every pair of distinct vertices x and y is joined by a unique path. Then first G is connected. Notice that here we don't assume G is connected at the very beginning. Okay, this is a corollary can be derived from the property. Okay, so first G is connected, then if G is not a tree, then still by theorem B, there is a cycle. Then this is a direction, because whenever you have cycle, you have two paths connecting a certain pair of vertices. Okay. So remark. So this property is very good because for a tree, you have very clear minimizer for the length functional. So this path, gamma, is shortest path joining x and y. And in particular, the distance between x and y is, let's recall the definition. This is all the paths L joining, path gamma joining x and y, and you take the length of gamma. Oh, sorry, this is not a summation, minimal. Okay, and for a tree, then this is easy. This is realized by the unique path gamma. Okay. In general, this is not true, especially for the infinite graph. So it's a hard problem to find a minimizer. And sometimes you may have no minimizer at all. You have a sequence of paths just approach the length, but there's no minimizer if you have some weight. We will talk about this phenomena when we discuss networks. Okay, and theorem B actually is very interesting because for certain graphs, you don't need to do any numerical calculation at all. And from the picture, you can tell this is not a tree. Just like this one, because here you have a cycle, so not a tree. Okay, after we discuss the characterization of trees, then a natural question is, so what is the number of trees or a graph or order n? So in other words, let's call this Tn. So in other words, suppose you have fixed endpoints, and how many trees you can draw among those vertices. So for T1, this is easy. You have 1. And for T2, it's also easy. You have to connect these 2 points. And for T3, you still have only 1 choice. And then for T4, as we showed before, now you have 2 choices. And then for T5, you have the following 3 choices. Okay, for 6, you have six choices as follows. You will notice that actually this is quite similar to the partition or integers. If you have interest, you can search online, like what is total number of trees among m vertices. Okay, blah blah. Okay, and before we get into another more interesting property, which asks not from the outside, the extended version, just from the reduced version, which asks for, suppose you are given certain graph, how many trees contained in this graph as a subgraph. So this is more it's an example contain more information, because for the problem we discuss here, how many trees among empty graph only have vertices without any edges. This is kind of a vacuum state. You don't have any information. Okay, doesn't depend on your graph. Okay, in reality, we always have some concrete example, and we want to do some analysis of it. Okay, before that, we make some definitions. So first definition is pendant vertex a tree or a graph G is a vertex whose degree is 1. So any edge incident with a pendant vertex is called pendant edge. Notice that for a pendant edge, you only require one of its endpoints. Endpoint is pendant vertex. Okay. For example, so this one is a pendant edge because one of its endpoints is pendant. And then a theorem says if G is a tree of order n, then G has at least two pendant vertices and at most n minus one pendant vertices. Also, we first proved the second claim, but the idea is similar. So let G is VE and V is kinetic of V is n, kinetic of E is m minus 1. Then let's compute the total degree of V. Then this is 2 times kinetic of E, which is 2m minus 1. Okay, then cannot have n, G cannot have n pendant vertices because otherwise the total degree of V should be 1 plus 1 plus all the way to 1, which is n, so less than 2m minus 1. Oh, here I should assume, oh yeah, here, okay, here a little bit of subtlety because I leave it to you. Because here when n equals 2, the inequality actually can be an equality. So you need to exclude this case. It's not a big issue because for higher dimension, when n greater than or equal to 3, this never happens. Okay, and the second case is, so therefore from 1 we know that you at most have m minus 1 pendant vertices, and then by 2, G has at least 2 pendant vertices. Otherwise, the total degree of V is greater than or equal to 2 times m minus 1 plus 1. So 2m minus 1. It's greater than, strictly than 2m minus 1, which is a contradiction. Okay, after we have this bound, a natural question is, what is the smallest and largest number of pendant vertices? A tree of order n can have. So you need to give some examples, and here the example. Here the example of first 2 pendant vertices is given by a line. So this is 2 pendant vertices. And then for the n-1, you just fix one point in the middle and connect to the remaining n-1. So n-1 pendant vertices. So this also has a name, star. Okay, then we will discuss the way to construct trees. So here first, we consider the spanning trees, just like you have a fixed ambient graph and you want to get rid of certain edges so that the remaining subgraph is a tree. So let G be a connected graph. And if G is not a tree, then it has a non-bridge edge. So removing a non-bridge edge, non-bridge edge, we get a subgraph G1. Repeat this procedure until we get a spanning subgraph. So spanning means they share the same vertices set, or G, which is a tree. And then we call such tree spanning tree, OG. And an immediate remark is spanning tree is not unique. So after we have some concept, we always want to show that this concept makes sense. Okay, so the following theorem says every connected graph, a general graph is the same thing, has a spanning tree. So proof. Actually, the proof we can follows from the following algorithm for a spanning tree. Okay, let G be a connected graph of order n. So this is initial data, and then set f equals e. And then secondly, while there is an edge alpha of f such that alpha is not a bridge of the graph, t equals vf, then we remove alpha from f. Okay, then the terminal. Since every time we decrease cardinality or the edge set by 1, so after finite step, the program must stop. So the terminal graph T is a spanning tree, OG. Okay, so we are done. And the remark is that, as we said before, the algorithm works for general graph as well. Why? Because in general graph, the only difference is that you might have a multiplicity for each edge. You have multiple edge connecting the same pair of points. Then you can take repeatedly those edge and remove it from the edge set. Or you might have some loop around the same point. And according to our definition, this is also a non-bridge edge. You can also remove it. So this algorithm, what does this algorithm do at first? Might be just reduce your general graph to a simple graph. Okay, and now let's look at one example which shows how this pattern works. So first step, we can, so when you remove some bridge, how to tell a bridge? Usually we just break cycles. So here you notice you have one cycle in the square, so break it. You can have this, and then you have another cycle. You can also break it. Okay, you have this case. Different way of breaking cycles give you different trees. Okay, and later on we will study the algorithm, how to generate trees and how to search on trees. And one important theorem we are going to prove is that when you go from one tree to another one, usually just like permutation, you just change one number or permute a pair of numbers. So here in tree, you just remove one edge and add another one. So how this possible? So we have the following two theorems. So let T be a spanning tree of a connected graph G. Let alpha be an edge of G, get rid of T. Then there is an edge beta of T such that T prime defined by V and E plus alpha minus beta is also a spanning tree OG. So first, let's give some illustration of this theorem. So this theorem says if you have tree and you have a new edge outside of this tree, okay, and you want to add this in, kick this in, then you need to kick something out. You need to kick something out. So here, this theorem says you can always do that. Whenever you want to kick something in, you can find something kick out. Okay. So later on, the next theorem which says whenever you want to kick something out, you can always kick something in. So they are complementary to each other. So prove. So let's consider t hat, which is a graph obtained by adding alpha to t. Then there is a cycle gamma in t hat containing alpha. Why this is true? Because t is a tree. So suppose alpha joins A and B, and since t is a tree, there's another path in t joining A and B. So use that path and alpha, you get a cycle. And then take an edge beta in gamma, which is different from alpha. Let t prime be the set obtained from t hat by deleting beta. Then first thing is we have the correct number of edges for this to be a tree, and then most importantly, t prime is connected. So for connectivity, you need to prove this, but it's not that hard. Okay, then we're done. The next theorem, just as we illustrated before, this is just a reverse direction. You first kick out something, and then you want to find something to make it up. You want to kick it in. So let T1 and T2 be spanning trees or connected graph G. Let beta be an edge of T1. Then there is an edge alpha of T2 such that the graph obtained from T1 by inserting alpha and deleting beta is a spanning tree of G. So prove remove beta from T1. We have T1 hat defined by this. Okay, so this is subgraph. Then T1 hat has two connected components, T1 hat prime, T1 hat double prime. Since T2 is spanning, it's a spanning tree. Okay, then there is an edge alpha in T2 such that alpha joins vertices, joins a vertex in T1 head prime and a vertex in T2 head prime, and then consider T head, which is defined by removing beta, adding alpha, then the number of edges satisfies the requirement for a tree, and T head is connected. Then by the definition, T is a spanning tree OG. So we're done. So the remark, a graphic illustration, which is similar as before, that if you want to kick some edge out, then the theorem guarantee an edge, just make it up, can be kicked in. Okay, and let me see. I forgot to mention another easy way to grow in trees. So we start with a single vertex and iteratively choose a new vertex and put in a new edge, joining the new vertex. Actually, you can cook up the algorithm by yourself. So here I just use an example to illustrate this. So you start with a single point, and after that, you find an edge connecting to a new vertex, and then you find another new vertex connected to, and you repeat this procedure until you put in all the vertices. So this is a generation from an empty ambient space, empty, just a vacuum state you just build up. And then the spanning tree version, you have some fancy building and you just destroy it until it has some skeleton. Okay, you just take off all the fancy non-necessary stuff so that it's as simple as possible but still connected. It's still a house you can still live in, but without any fancy stuff. Okay. And one immediately interesting question is, what is the number of spanning trees or a connected graph? So let's call this TG. G is graph. And we already have some discussion. And so here, let's look at another example. You have square, and the way to disjoint two spanning trees, you can have the following 4 cases. And example 2. For example 2, it's much harder that you can either work out by yourself or just look at the Wikipedia, search for related materials if you have interest in this. This is for complete graphs. Cayley proved that the total number is n to n minus 2's power. And then for Qn is a hypercube, just appear in the Gary code. So this number is 2 to 2m minus n minus 1 times product for k from 2 to n, k to n, choose k's power. Okay, and in general, we have the Kirchhoff theorem. Suppose G is connected. Kirchhoff is an engineering and a physicist. Connected graph of order n, and define its Laplacian matrix as follows. The Laplacian matrix Lij, 1 less than I less than j, 1 less I than less than n. So this is an n by n square matrix. And how to define it? So Lii is a degree of i's vertex, and Lij is for I different from j is 1 if i's vertex is adjacent to j's vertex, 0 otherwise. Oh, here I should say, in this case, we care about simple graph instead of general graphs. Okay, then let lambda 1, lambda 2, lambda n minus 1 be the non-zero eigenvalues of L, the Laplacian matrix. Then Tg, the total number is 1 over n times lambda 1 times lambda 2 times lambda n minus 1. Yeah, this is a very fantastic formula, and if you apply to the previous case for Kn and Qn, you expect the answer derived previous by other people. And you can foresee the difficulty of this formula is that when you have a quite large graph, for example, you have 20 vertices, not that large, but then for this problem, you need to diagonalize the 20 by 20 matrix. In general, this might be a difficult task. Okay, and if you are interested, you can search online for more details. And another similar question is, we look at the example, we will find that These actually are isomorphic trees. So they are isomorphic. I hope you still remember what does isomorphism mean. So that means you can have a map between vertices and edges so that you transform one graph into another one. Okay, so a similar question is what is the number of non-isomorphic trees of order n? So we call this mu g. So for this question, it's more subtle, but fortunately we have certain inductive formula. So let a0 be 0 and an plus 1 be 1 over n times summation for k from 1 to n, summation all divisors of k dad times an minus k plus 1. And then you cook up the generating function tx by summation of ai xi, and let small tx be 1 plus capital Tx minus 1/2 tx squared minus tx squared as a variable, and then mu g. Okay, so sorry, here you should have superscript to denote g, to denote n. This is the coefficient of xn in Tx. Okay, so that's it. We'll stop here for this lecture.